Hello everyone, today we're going to look at simplifying radical expressions. We became familiar with them in a previous video. Now we're going to learn how to do some operations on them. And the first thing that we need to specify is that if both the nth root of x and the nth root of y are real numbers, that just means we don't need to worry about any situation arising where either one of these becomes not a real number. So that is taken care of. And then for all n belonging to the set of natural numbers, so we want the index to be a natural number. Of course, you know the set of natural numbers are also known as the set of counting numbers, numbers you can count on your fingers, like 1, 2, 3, etc. And we're usually interested in n values larger than 1, because if n is 1, you just get the first root of a number, and the first root of a number is just itself. So all this makes the most amount of sense when n is greater than 1. But for the purposes of generality, we can say all natural numbers. However, we'll be using mostly n values larger than 1. Now, one nice thing that we can do is if we have two nth roots, notice the index needs to be the same, and we multiply two expressions like this, which are both nth roots, then we can go ahead and multiply under the radical in this way, and we can also divide under the radical. So we get the nth root of x equals the nth root of y equals the nth root of x over y. Now, these can be really handy. Just to show you a quick example to let this sink in. For example, let's say we have the square root of 8 times the square root of 2. Now, as you know, neither the square root of 8 is a rational number, nor is the square root of 2. But here's an interesting that happens. Given the rule above, we can go ahead and multiply those two, and we get the square root of 16, which is 4, which of course is a rational number. So mathematically speaking, this means the set of irrational numbers is not closed under multiplication, because we can multiply two irrational numbers and end up with a number that is not irrational. So mathematically speaking, we say the set is not closed under multiplication. But that kind of topic becomes interesting for you only if you continue on in more advanced mathematics. For our purposes, we just know that we can go ahead and multiply under the radical whenever the indexes are the same. We can also divide. For example, let's say we have the cube root of 250 over the cube root of 2. We can go ahead and divide those. Since the indices or indexes are the same, both of those words can be used for the plural of index, and we end up with the cube root of 125, which, as we know, is just a nice 5. Of course, those I'm trying to extend. It's not like a minus sign or anything like that. And we know that becomes 5. So that is also possible because the indexes here are the same. You cannot do that if these two indexes or these two are different. So it's extremely important to pay attention to the fact that you can only multiply or divide under the radical if both indexes are the same. Of course, we don't always end up with nice rational numbers. For example, if I multiply the square root of, say, 2 by the square root of 3, yeah, I'm still going to be able to multiply under the radical, and I just get another irrational number, but that's fine as well. Or let's say we have some variables. Let's say I have the square root of 3x y times the square root of 4z. because both of those are square roots and they have the same index 2, we can go ahead and multiply under the radical, and we get the square root of 12x, y, z. So that's possible as well. And of course, this works for higher roots as well. Let's say we have the cube root of 7u times the cube root of 2v. Again, because the indices are the same, we can go ahead and say that's equal to the cube root of 14uv. And of course, this works with all higher level roots as well. And we can also use the quotient rule. For example, let's say we have the square root of 11 over 7. We can always break that up as the square root of 11 over the square root of 7. Or let's say we have the cube root of 27 over 5. Now we can go ahead and break that up in this way, and we end up with 3 over the cube root of 5. By the end of this lecture, we'll learn how to actually not leave an answer like that, but right now we just want to explore the possibility that it's doable. But we'll get to how to simplify something like that through what's called rationalizing the denominator soon. Of great interest to us is making sure that whatever the index is, we don't leave any perfect powers of that index under the radical. So for example, here we notice that this, if we break it up as the square root of x to the 8 over the square root of 121, we end up with x to the 4 over 11. So what if we have something like the square root of 44? Now we know there's a perfect square hiding inside 44. If we look at the prime factorization, which is going to be one of our best friends in this section, we know that we can start by the prime number 2 that goes into 44 22 times. 2 again goes into 22 11 times, and then 11 is prime, so the only number that'll go into it is 11 itself, and we get 1. Once we reach the 1 here, we're finished with the prime factorization process, and we can see the prime factorization of 44 right here. So we notice that we can write the square root of 44 as the square root of 2 squared times the square root of 11. And here we just applied the rule nth root of x times y equals nth root of x times the nth root of y. Notice that you should be comfortable using this rule in this direction or in the opposite direction. In this case, just to show you the exact details, let me go ahead and rewrite this in this way. Normally we won't show this step, but this is what we did. We said, okay, from the prime factorization, this is going to be 2 squared times 11. So we can write, instead of 44, we can write 2 squared times 11. Now we can go ahead and split it up using this rule as the square root of 2 squared times the square root of 11. And of course, what number do you square to get 2 squared? Of course, 2. And that's going to be multiplied times the square root of 11. And that is our final answer. So we normally don't even write the dot. So basically, any perfect square that was under the radical, we went ahead and we brought it out of the radical. That's called bringing the perfect squares out of the radical. So this rule that we spoke about last time, that the nth root of x to the n is equal to x, as long as it's a real number, then we realize that it's going to be extremely helpful to us in this section. So we're going to be applying that quite a bit. So even though that's a very simple example, that lays the foundation of what we're about to do from this point forward. So make sure, as simple as it is, you fully understand it before you proceed while I get the next board ready. Okay, the instruction for pretty much all the problems we're going to do in this section is going to be the same: simplify. So here we have the square root of 50, and here we have the cube root of 16. Let's start with the square root of 50. Go ahead, and again, if you think you can do this on your own, you should proceed and pause and try it. And when you come back, I'm hoping that you did the prime factorization of 50, which, as you know, we can start with 2, which goes into it 25 times, and then 5 goes into 25 5 times. Finally, 5 is a prime number, so it can only have itself as a factor, and we end up with the 1. So we can see this time that we can rewrite the square root of 50 as the square root of 5 squared times 2, which we can then break up as the square root of 5 squared times the square root of 2. So we end up with 5 radical 2. The more comfortable you are with numbers and the less dependent you've become on calculators, the quicker you'll be able to do this. So this method we're showing right here is very algorithmic, it's fail-proof, and even if you've let yourself become dependent on calculators, you can still follow this through. Now, for those of you who are really comfortable with numbers, the quick method, of course, would be to go ahead and take the square root of 50, and you can just think in your head, what's the biggest perfect square factor of 50? And you'll realize that's 25, so you can write it as the square root of 25 times the square root of 2, and you end up with the same 5 radical 2. So whichever method works for you, they're both fine. So this time we're going to look at the cube root of 16 on the right here, and again, if you're comfortable enough, you can use the quick method, but if you are not, you can always look at the prime factorization of 16, which, as you know, we have 2 that goes into it 8 times, 2 again 4 times, 2 again 2 times, and finally one more 2 gives us 1. Now, it's important to note that this time we're trying to simplify a cube root. So we're not looking for a perfect square in the factorization of 16. We're looking for a perfect cube that we can bring out of the radical. So, and we notice there is one perfect cube in there. So we can go ahead and break this up. So as the cube root of, you can either write 2 cubed or you can write 8, makes no difference. It's easier to go ahead and write it as 2 cubed, and then you have the cube root of 2 that's left. So this 2 that you see here is the one that was left after the 2 cubed was taken out. So now we know what the cube root of 2 cubed is. Remember, this should be like automatic for you. The nth root of x to the n is x. Okay, so as long as, of course, we're dealing with situations which do not cause problems with this expression. That's why we had this stipulation that these should be real numbers. Okay, so here we end up with 2 times the cube root of 2. Like that. Now, the quick method here would be the cube root of 16 equals the cube root of, the question you ask yourself, what's the largest perfect cube factor of 16? And you realize that that's 8, so you go times the cube root of 2 like that, and you end up with 2 times the cube root of 2. When you're trying to type these into a computer homework system such as my MATLAB, make sure that you put the index 3 in there, otherwise it's going to count it as wrong and you're going to be disappointed. So notice the trick that we're using is basically we're splitting up one radical using the rule that says the nth root of x times y equals the nth root of x times the nth root of y into two radicals like this. Now, the way we do it is in the first radical, we go ahead and put the perfect powers, such as here it'll be the perfect cubes, and in the other one we'll put the non-perfect cubes. Back here in the previous problem, in the first radical we put the perfect squares, and in the second radical we put the non-perfect square factors of the original number. And in this way we can simplify these radical expressions very nicely. Make sure you absorb this before we proceed. And remember the trick. Write the problems down on a blank piece of paper. See if you can go through and do it on your own. This is the only way to make real progress in your mathematics while I prepare the next board. Okay, next we'll look at a couple of problems which have variables in them. The strategy is going to be exactly the same. So we're going to break these up into two parts. This is a square root, so under one radical we're going to put the perfect square part of 200 x cubed, and in the next radical we're going to put the non-perfect square part. So to accomplish that, if you are comfortable enough with math and numbers, you may know what the biggest perfect square factor of 200 is. It's actually a pretty simple number, but in case you're not, let's go ahead and find the prime factorization of 200 anyway. So we know that we can start, since it ends in 0, we know 2 is going to go into it. So we're going to go ahead and start with 2. That's going to give us 100. 2 goes again into 150 times. And 2 goes into 50 25 times. Now we have to move up to 5. Make sure you always check for divisibility by 3 before you jump to 5, so that these numbers here will be nicely ordered for you from the smallest to the largest. So we know that 3 doesn't go into 25 because 2 plus 5 is 7. So we go ahead and move on to 5, which we know goes into 25 5 times, and finally 5 goes into itself 1 time. So we have the prime factorization of 200 right here, and we can see that there's a perfect square there and a perfect square here. So in the perfect square radical for the factorization of 200x cubed, we're going to put 2 squared times 5 squared, and immediately in the non-perfect square part we'll put the 2 that's left over so that we don't forget it. Okay, so that's going to be in there by itself. Now we deal with the x cube. Now these are actually the easiest part, because when you see a power like that, that's already in factored form. So how much of this x cube is a perfect square? Well, let's take a look down here together. We know x cube is x times x times x, right? So the part that's perfect square is like right there. Interesting enough, you could even do a prime factorization like this. We know x goes into x cubed x squared times. Again, x goes into it x times, and then x goes into it once. So you can even do that, but as you can see, that's not really necessary. But if you wanted to, you could do it. So we're going to put x squared in the perfect square radical, and we're going to put what the x, so this x squared is going in here in the perfect square radical, and in the non-perfect square radical we're going to put just x that's left over. So now we know that the square root of 2 squared is of course 2, the square root of 5 squared is 5, and the square root of x squared is just x. Notice those have now come out of the radical. We've applied the square root to those, and this is what we come up with, 2 times 5 times x. And of course, we still have a radical 2x. Now, if we clean that up, we end up with 10x radical 2x. And that is the simplified form of the square root of 200x cubed. Notice any perfect square that was hidden inside it has now been separated and has come out of the radical. Because after all, the square root of a perfect square should be a nice simple number, as we can see here. So that's how you do these problems even when they have variables in them, no different than when we just had constants. So now let's go ahead and try the next one. As always, please try it on your own first before you unpause the video and come back. All right, so this time. Now, first of all, we know that an odd root of a negative number is going to be a negative number. So why don't we go ahead and take care of that and bring the negative out so we don't need to worry about it anymore. And also we don't forget it. So this time we're gonna break that expression into two radicals again. This time we're gonna have perfect cubes in this one, and in the next one, cube root, we're gonna put the non-perfect cubes. So 16, if we look at it, we know we can start with 2, which goes into it 8 times. 2 again will give us 4. 2 again gives us 2. Finally, one more 2 gives us 1. So on the left here, right here, we have the prime factorization of 16. So 16 is 2 to the power of 4. As you can see, there is a perfect cube that was hiding inside 16. So we can go ahead and put the perfect cube in here, so 2 cubed. And of course, we're left with a 2 that goes in the non-perfect cube radical. Now notice that we have x to the 7 that we need to deal with. So how much of x to the 7 is a perfect cube, right? Well, if you actually wrote it out, it would make perfect sense to you. We have 7 factors of x, right? Like that. Notice each 3 of them will be a perfect cube. So for a total of how many? X to the 6. So we're going to put x to the 6 in here, and we're left with one more x that we need to put in the next radical. So we end up with, now what is the cube root of 2 cubed? If you remember, the nth root of x to the n is x, as long as the nth root of x to the n is a real number, which if you remember from the beginning of the lecture, we're assuming. So that's going to give us 2. And the cube root of x to the 6, what number do you have to cube to get x to the 6? You have to remember the power rule for that. In other words, what expression cubed will give us x to the 6? And if you think about it, that better be x to the what? Exactly, 2, because you know the power rule says that you have to multiply those exponents. So the easiest way to actually answer that question is just to go ahead and divide 6 by 3. So we get x squared times the cube root of 2x. Once again, make sure you don't forget to put the index 3 for a problem like this, because otherwise it would not be considered correct. So these are 2 good examples. Make sure you fully absorb them, write them out in case you haven't already done it on your own. Do them on your own without looking, and then continue. One quick note that I want to make for you here before we erase this board and go to the next board. Notice that the best way to figure out what is the biggest perfect cube inside a power like this is to ask the simple question, what is the largest multiple of 3 less than or equal to that number, right? And if you think about it, 3 times 1 is 3, 3 times 2 is 6. And if you go 3 times 3, you've gone too far. So we know that 3 times 2, which is 6, is going to be the power that we want in here. So always look for the largest multiple of the index less than or equal to the exponent of the power that you're dealing with. And that is how you can quickly get that 6 instead of having to do this. Obviously, we did this here because this was the first problem we were looking at together, and because the power wasn't that large, it was only 7. Imagine it was 700 or something like that. You wouldn't want to sit here and write 700 factors of x, would you? So we better have an efficient way of dealing with that. And what we just discussed, which is to look for the largest multiple of the index less than or equal to that number, that exponent, is the most efficient way to approach that. So go ahead and completely absorb this before we continue. Okay, so here we have a couple of more problems to look at before we go on to other types of simplification. Notice that we said that we usually divide these radicals into two parts: the perfect nth power radical and then the non-perfect, whatever that nth power is. But sometimes every factor inside here is a perfect power of that number, that index. In those cases, you don't really need to break it up into two parts. And notice here, 16 is a perfect fourth power, x to the 8 is a perfect fourth power, so is y to the 12. So in this case, we can just go ahead and write out the answer in one simple move. We know that the fourth root of 16 is 2. The number you need, or the expression you need to raise to the power of 4 to get x to the 8 is x squared. Remember, the easiest way to get that, just divide 8 by 4 and you know what should go here. And that's because of the power rule. And the expression you need to raise to the power of 4 to get y to the 12 is, of course, y cubed. And that was an example of a perfect fourth power expression under the radical, which is, of course, not going to require you to break it up into two radicals. How about this one? Go ahead and try it before you come to see me do it with you. So try it on your own first, then come back. All right, so we'll come back. I'm pretty sure you did realize we definitely do need to break this up into perfect fifth powers. And non-perfect fifth powers. So let's look at 64 and see what's hiding in there. We can start with 2, and you may remember this from your table anyway, so that I asked you to memorize. We know that that goes into 64 32 times, 2 again 16 times, 2 again 8 times, 2 again 4 times, 2 again twice, and 2 1. So as you recall from the table that you were asked to memorize previously, 64 is in fact 2 to the 6. So yes, in fact, there is a perfect fifth power hiding inside 64, and that's 2 to the 5, which is also known as 32. So here you could write 2 to the 5, or you could have written 32. Makes no difference. And of course, there's a make sure you have the index on both of them, and there's going to be a 2 left, which we need to put in the non-perfect fifth power radical. And x cubed, what's the largest perfect fifth power inside x cubed? Well, there isn't any. X cubed is just x times x times x. There's no perfect fifth power hiding inside there. So all of x cubed will go in here in the next radical. How about y to the 21? Remember the trick? Ask yourself, what is the biggest multiple of 5 less than or equal to 21? And I'm sure you realize that that's going to be 20. So we're going to put y to the 20 in this radical, and we will put the y that's left over into the non-perfect fifth power radical. Z to the 19, So what is the largest multiple of 5 less than or equal to 19? I think you'll agree that would be 15. So we'll have z to the 15 go in here. And what's left now? Z to the 4. And now we're just going to simplify. So we know that the 5th root of 2 to the 5th is just 2. The 5th root of y to the 20, remember the trick, just divide. What's 20 divided by 5? 4. So y to the 4. The next one, z to the 15 over 5, that's going to be z cubed. And then we have the 5th root of 2x cubed y z to the 4, and that's just going to stay with us because there's no more perfect 5th power that we can remove there. So there you have it. That's as simple as these are. You just have to be careful. Again, make sure you write each of these down on a piece of paper and try to do them on your own without looking, and make sure you get the same answer before you proceed. So here's an example that we can actually simplify by reducing the index here. And the way that works out is we're going to go from this radical form to rational exponent form or fractional exponent form. We're going to reduce the fraction and see what happens. So we're going to get 2, if you remember the rule, when you have the nth root of b to the m, recall the root, it's b to the power of m over n. So using this rule, we get 2 to the power of 4 over 12, which is, now this can be reduced, right? So we get 4 goes into 4 once, into 12 3 times. So we end up with 2 to the 1/3, which we can now write as the cube root of 2. So there's a nice operation involving rational exponents from the previous video that we looked at. These rational exponents can also come in handy if you end up with a situation like, let's say, the square root of 2 times the cube root of 2. Now, as you know, these indices are different, so we cannot use the nth root of x times the nth root of y equals the nth root of xy rule, because this rule can only be applied if both of these indexes are the same. So, but this doesn't mean there's nothing that can be done here. Notice that we can use our friend here, the rational exponent conversion formula, to get something done and simplify this. So we can say that's 2 to the 1/2, again from this rule, with m being 1 here. Remember, 2 to the 1, and n being 2. So that's why you get 2 to the m over n, which is 1 over 2, times 2 to the, here we're going to get, again, the exponent here is 1, so we're going to get 1 over 3. So times 2 to the 1/3. Now we realize, oh, we have 2 powers with the same base, even though they don't look the same here. That looks better. So we have two, we're multiplying 2 powers with the same base. So we remember our product rule, which is x to the m times x to the n equals x to the m plus n, if you recall. So here we're going to get the base 2, which always stays the same, and then we're going to add 1/2 and 1/3. In all the laws of exponents we've studied, there's only one law in which the base disappears, and that's x to the 0, which becomes 1. Otherwise, any rule of exponents that involves a base, the base never changes. Okay, so here we're going to need a common denominator 6. So we're going to have to multiply this denominator by 3, so we'll have to do the same to that numerator. This denominator we're going to multiply by 2, so we have to do the same to the numerator as well. So we end up with 3 plus 2 on the top, and that's going to be 2 to the power of 5/6, which we can now write as the 6th root of 2 to the 5, or the 6th root of 32. So that's how you handle a situation like that where the indices are different. You have to go back to your rational exponent rule for some help there. So make sure you can do that on your own before we proceed. Let's do one more of those. Of course, in the last example, I used 2 as the radicand in both cases. That they don't always have to be the same. For example, what if we have the cube root of 5 times the 4th root of, say, 7? Can we still apply this rule? Not exactly in the same manner, but there is something we can do here. Notice we can write the first radical as 5 to the 1/3, and we can write the second one as 7 to the 1/4. Now, currently, those denominators are different, but notice if we actually go ahead and make them the same, namely the LCD, which is 12. So I'm going to multiply this one by 4, which means I have to do the same on the top. I'm going to multiply this one by 3, which means I'm going to do the same on the top, correct? So now I basically have 5 to the 4/12 times 7 to the 3/12, right? Now what we can do is we've basically exhausted how much help we're going to get from rational exponents. We're going to go back to radical form now, because now we realize the 5 to the 4/12 we can write as the 12th root of 5 to the 4, and the 7 to the 3/12 we can write as the 12th root of 7 cubed. And now, because we now have the same index, we can go ahead and multiply under the radical. So we're going to end up with the 12th root of 5 to the 4 times 7 cubed. All right, so this is the point at which we thank God for the existence of calculators. And we will go ahead and use this beautiful calculator courtesy of HP. Amazingly made freely available. And we multiply 5 to the power of 4. Actually, that didn't go through. Let's try that again. To the power of 4 times, I had to, I think, move. Yeah, this is a little bit getting used to. Times 7 to the power of 3. And we end up with the 12th root of 214,000. Let me see that again. 375. So that is how you simplify a problem like that, well, where the indices are completely different and the radicands are not related either. So, but we can still use some nice algebraic tricks to bring this and turn this into just one radical. So make sure you can actually do that on your own before you proceed. All right, next we want to take a look at the famous Pythagorean Theorem. That's one of the situations in which simplifying these radicals comes up quite often. So um, a lot of you, when you hear the phrase the Pythagorean theorem, you may be thinking a squared plus b squared equals c squared. Uh, in many senses, you are correct, but I have found out that thinking of it that way can get students in trouble. Here's an example why. See, as long as we have a right triangle and the legs are A and B and the hypotenuse is C, there's no problem with saying A squared plus B squared equals, in fact, C squared, because that's what the Pythagorean theorem states. It says the sum of the squares of the legs of a right triangle is equal to the square of the largest side, which is called the hypotenuse. So where I found students get in trouble with that is sometimes they get thrown a problem like this. Actually, I can use ink to shape, I believe. Let me try that. Let's see if it works this time. Well, it did it that way, but I can use this. Let's say I have a right triangle like this, right? And let's say that's where A, B, and C are, see? Now notice this time, the hypotenuse is A. So if you say A squared plus B squared equals C squared here, you would be wrong. Okay? So this is why I actually don't use the A squared plus B squared equals C squared terminology anymore. Notice that the correct thing to say for this triangle would be that B squared plus C squared equals A squared. So to avoid all that, I basically do the following. I don't know why it keeps liking to make it like that. Let me try it before I... Okay, it looks like Microsoft really needs to still work on that ink to shape business, so I'm just going to give up on it and turn it off. So the way that I like to represent the Pythagorean theorem to you is this way. It'll be safer. If we just call, remember, the two sides of a right triangle that form the right angle, they're called the legs. This other side is called the hypotenuse. So basically what I like to do is call this one L1 and this one L2 and use H for that one. This way it's safer, we can't go wrong. So we know that leg 1 squared plus leg 2 squared equals the hypotenuse squared. And with that terminology, we can't go wrong. So let's go ahead and take a look at an application together. Okay, let's say that we're given this problem and asked to find x in the figure to the left. Of course, one approach to do what one of my students did one time and said, here is x, right? And as clever as that is, that won't get you too many points. So let's go ahead and try it using the Pythagorean theorem instead. All right, so remember that we're going to use L1 squared plus L2 squared equals H squared. My recommendation to you is, if you're going to use a formula in mathematics, always write the formula as is. Don't start plugging in. That's how students get in trouble. And then substitute. So we know that, for example, we can think of this one as L1. We can think of this leg as L2. They're the two sides that form the right angle, so they're the legs. And the largest side, which is opposite the largest angle, which is 90 degrees, is x. And why is that the largest angle? Because remember, all three angles have to add up to 180. So if this one is 90, that means those of two together have to add up to 90. So there's no way either one of them can be 90 or more. So that's how we know this is the largest angle. And as you know, in a triangle, the largest side is always opposite the largest angle. So we know that's the hypotenuse. So that's what plays the role of h here. So we're going to end up with 5 squared plus 10 squared equals h squared. So that gives us 25 plus 100 equals h squared, and 125 equals h squared. So when we go to the next step, we have to look for the number that we have to square to get 125. And of course we know that's going to be the square root of 125. But if you recall, there are actually two numbers that do that. One is the positive square root of 125 and the other is the negative square root of 125. So if this were not a physical problem, we would write this as the correct answer. But here, because h is the length of a real physical object, it can't be negative because length is never negative. So here we're going to go ahead and reject this because length is always greater than or equal to 0. So we have h equals square root of 125, and of course we never want to leave any mathematical problem unsimplified, so we're going to try to reduce that. So we're going to go ahead and factor 125. We know that 3 doesn't go into it because 1 plus 2 is 3 plus 5 is 8. So we go ahead and move up to 5. We always check for 3 before we move to 5, so we don't miss any prime factors, and we end up with 25. We know 5 goes again into that 5 times, and finally another 5 gives us 1. So we can break this up. Remember, we put the perfect square part here and the non-perfect square part in the next radical. And of course the perfect square part is just going to be 5 squared or 25, and what's left is 5. And we know that the square root of 25 or 5 squared is 5, so we get 5 radical 5. So for the final answer, we're just going to write h equals 5 radical 5. So simple enough. Make sure you can do it on your own before we move on. So in this next segment, which is the last segment for today, we're going to try to find the distance between 2 points in a plane. And so we're labeling one of the points the point x1, y1, and the other one x2, y2, so that we can be as general about this situation as possible. So this is one of those situations where the Pythagorean theorem is going to help us quite a bit. Notice that given two such points in the plane, there are two natural triangles we can form. One is if we go straight up here and then to the right, and the other one is if we go straight down and to the left. And either one works because those two triangles are going to be congruent. So let me just go ahead and use this one because there's more space here. So we're going to have a triangle like this, right? So the point is, we need to find the length of these two legs. And if you notice, if this is the point x1, y1, that means this point here is x1 on the x-axis, this point here is y1 on the y-axis, and this point here is going to correspond to x2 because that's the x coordinate of that point, and that means the point here on the y-axis is going to be y2. So I know that if I'm just looking at the x-axis, if I want to know the distance between 2 points, let's for example say this is 3 and that's 7. Well, how would you find that distance? All of you would go, oh, that's 4. But do you realize what you do? You subtract the smaller from the larger. So you go x2 minus x1. So we know that this distance here is x2 minus x1. And of course, the y-axis is just another number line. So it behaves exactly the same way. And this is larger, this is smaller. So we can go y2 minus y1 to get that length. And also realize that this length right here is going to be the same as that on this right triangle, this leg on this right triangle. So that means this leg is y2 minus y1, and this leg here is going to be x2 minus x1. And of course, the hypotenuse is going to be the distance, exactly the distance I'm looking for. So let's go ahead and use the Pythagorean theorem, which says, I'm going to start it with h squared equals L1 squared plus L2 squared. So the length of the hypotenuse squared is equal to the sum of the squares of the lengths of the two legs. And here h is just going to be d. So we get d squared equals, notice L1, we can just call it this one, x2 minus x1 squared. So x2 minus x1 squared plus L2, which is this leg, which is going to be y2 minus y1. And then that's going to get squared. So now we know that if we have d squared, but we want d, so what are we going to do? We're going to take the square root of the expression on the right. So we're going to get d equals, again, normally it would be plus or minus the square root, but since we're looking for a positive distance right here, we're just going to take the positive square root. So we're going to get d equals the square root of x2 minus x1 squared plus y2 minus y1 squared. And that right there is called the distance formula. So a very nice simple application of the Pythagorean theorem is finding the distance between any 2 points in the plane. So next, what we would like to do is go ahead and find an actual distance between 2 points that are known rather than just 2 general points. So make sure you understand this before we do that. Okay, now let's say we want to find the distance between these 2 points, -3, 2, and 2, -3. Even though we don't actually need the graph of the situation, we have presented it here just so that you have an idea of what you're actually finding. You're trying to find this distance. So we're going to go ahead and just call this point x1, y1, and this one x2, y2. Makes no difference actually which one you call which of those pairs. And now we're going to go ahead and write the distance formula down. Remember, if you're going to use the formula in mathematics, write it down as it is without plugging anything in. So we want the square root of x2 minus x1 squared plus y2 minus y1 squared. And now we're just going to go ahead and substitute our values. So for x2 right here, we're going to use 2 open parentheses 2 minus x1, and be very careful here, x1 is -3, so we're going to put it in a smaller set of parentheses, then we're going to close the larger parentheses and square, plus we're going to do the same with y2, so -3 minus y1, which is 2 squared, correct? So now we're just going to proceed with simplifying that. And here we realize 2 minus -3 just becomes 2 plus 3, so that's 5 squared. And we know -3 minus 2 is -5, so here we get quantity -5 squared. So that's going to be the square root of 25 plus another 25, which is the square root of 50. And I think you know by now we can split that up into 2 parts. What's the biggest perfect square factor of 50. You can either do prime factorization or without it, depending on how comfortable you are with math. Here we get 5, 5, 5, 1. So now we have a perfect square of 5, so 25 can go in here, and we're left with 2. So the distance between those two is 5 radical 2. We haven't given any units. It could be given, but if it's not, you can just say units. Usually in applications like my MATLAB, you're just going to type 5 radical 2. And that's basically how you do these distance problems. And that pretty much wraps up our section today, which dealt with simplifying radical expressions. And we're going to continue with this in our next video with further simplification of radical expressions. So be safe until our next meeting.